Hello, my name is Cliff Cummings and I am VP of Training at Paradigm Works and founder of Sunburst Design. On behalf of myself and my expert verification co-authors, Stephen Donofrio and Jeff Wilcox from Paradigm Works, and Heath Chambers from HMC Design Verification, we welcome you to this presentation entitled Advanced UVM Multi-Interface Reactive Stimulus Techniques. Let's get started. In our DVCon 2020 reactive stimulus paper, we showed the UVM built-in reactive stimulus technique that sends a sequence transaction through the sequencer driver and down to the DUT, and then the sampled response transaction is returned through the driver sequencer and passed back to the sequence, where it can be examined to help determine the next transaction to send. That technique can be found in the reference paper on the Sunburst Design website. This paper shows two additional reactive techniques. The first technique uses a UVM TLM analysis FIFO placed in the environment. That is the technique that will be shown in this presentation. And adding config objects and a virtual sequencer in the environment, also using a UVM TLM analysis FIFO. In this presentation, we will show the first technique and ask you to read the paper to find the second technique. The environment and the base sequence hold the keys to these techniques. We will build a UVM TLM analysis FIFO in the environment to capture the sampled outputs. Then the reactive sequence extended from a base sequence will get the sampled outputs from a transaction stored in the UVM TLM analysis FIFO. In this presentation, the terms UVM TLM analysis FIFO and TLM analysis FIFO will be used synonymously. For the reactive stimulus technique that we showed last year, a test starts a sequence on the environment agent sequencer, and the driver gets the transaction and passes it through the DUT interface and into the DUT. The driver then samples the DUT outputs and returns the sampled outputs in a response transaction through the sequencer and back to the sequence. The sequence then examines the outputs to possibly modify the next transaction to send to the DUT. A limitation of this technique is that the sequence might need to sample status bits from a different DUT interface, which is not covered by the single agent solution. A new technique described in this presentation also starts a sequence on the environment agent sequencer and again passes the transaction through the DUT interface and into the DUT. But then the monitor samples the inputs and outputs and places them in a transaction, and then broadcasts the sampled transaction through the analysis port and sends the transaction to a TLM analysis FIFO, which will queue up the transaction and hold it until the sequence retrieves the transaction from the TLM analysis FIFO. One advantage of this new technique is that it can be extended to multiple interfaces. Now status can be sent to a reactive sequence from a different transaction over a different interface. This capability is not available through the single agent solution that was shown last year. The example shown in this presentation is a simple test bench for a FIFO design. A more advanced example with config object and virtual sequencer is shown in the paper. A reactive sequence will be started by the test on the environment agent sequencer. Then the driver will get the transaction and drive it through the driver's virtual interface to the real FIFO interface and into the FIFO design. The monitor will then sample the FIFO1 inputs and outputs from the FIFO design and assemble the sampled transaction. The monitor then broadcasts the sampled transaction through the monitor and agent's analysis ports to the other components in the environment, including a response TLM analysis FIFO. At first glance, this appears to be a dangling TLM analysis FIFO that does not seem to have any value, but that is not true. Because the sequence has issued a blocking get command, it is waiting to retrieve the sample transaction from the TLM analysis FIFO. The sequence will then examine the status outputs that have been stored in the sample transaction, ignoring the sampled inputs, and determine what the next stimulus transaction should be and drive the updated stimulus back into the design. Just for completeness, the test1 class will be extended from a test base class, and the test base class needs to build just one component, the environment. The code for the test base and the test1 classes are shown on the next two slides. The test base extends from UVM test and declares the environment handle env. The test base then creates the environment in the build phase. All tests that extend from this test base will inherit the environment declaration and the corresponding build phase. The test1 class extends from the test base, which was shown on the previous slide. This test has inherited the environment handle from the test base and the build phase, which created the environment. There is no need to add the environment declaration or build phase to the extended tests. So the test base has simplified the creation of tests. For this simple example, the environment will participate in the build phase and will need to build 4 components: the FIFO agent, the FIFO coverage collector and scoreboard, and the response TLM analysis FIFO. This is new for this technique. The environment will also need to participate in the connect phase and will need to make 3 connections to the FIFO agent analysis port. The first 2 connections are from the agent to the coverage collector and the scoreboard, and the third connection is to the new TLM analysis FIFO, which appears to be a dangling component. The environment code is on the next 2 slides. Of course, the environment will extend from the UVM environment base class and will also make a UVM TLM analysis FIFO declaration with the handle name response TLM_AF. The environment will build all of the components, including the new response TLM FIFO, and then store the response TLM analysis FIFO handle into the UVM config DB. The sequence base class will retrieve this handle so that sequences can access the sample transactions from this response TLM analysis FIFO. The environment will also participate in the connect phase and will connect the agent's analysis port to the scoreboard, to the coverage collector, and to the analysis export input on the response TLM FIFO. Without knowing the big picture, this TLM analysis FIFO appears to be a dangling component with no obvious purpose. But the FIFO monitor will broadcast a sampled FIFO transaction to the scoreboard, the coverage collector, and most importantly, to the response TLM analysis FIFO. There is going to be a FIFO sequence base class that will retrieve the stored TLM analysis FIFO handle from the UVM config DB and copy it to a local response TLM analysis FIFO handle declared in the FIFO sequence base class. This will be shown later in the presentation. The FIFO seq base class will use a blocking response TLM analysis FIFO get command to retrieve a sampled FIFO transaction when it is available. The blocking get and the triggered event are in a separate fork join none loop that is started in the pre-start method of the FIFO seq base class, which will be shown on a later slide. As will be seen shortly, each sequence is extended from the FIFO seq base and will call command tasks that are also defined in the FIFO seq base class. As each command is executed, a reactive stimulus transaction is sent to the FIFO DUT, and then the command task waits until it sees the event trigger before the command task retrieves the sample transactions, examines the sample transaction output or status bits, then reacts to the status bits and calculates the next stimulus transaction to send to the DUT. The agent will need access to the FIFO interface handle, so the top module stores the DIF handle into the UVM config DB. So now looking at the FIFO agent, in the build phase, the FIFO agent will declare the VIF virtual interface handle and build three components: the sequencer, driver, and monitor, and the agent's analysis port. Still in the build phase, the agent will retrieve the DUT interface handle from the UVM config DB and save it to the VIF handle declared in the FIFO agent. Next, the agent needs to make two connections in the connect phase: the sequencer to the driver and the monitor analysis port to the agent analysis port. Then the agent copies its VIF handle to the driver's declared VIF handle and to the monitor's declared VIF handle. These next two slides show the FIFO agent code. The agent declares the virtual FIFO interface VIF handle and the handles for the analysis port, driver, monitor, and sequencer. Then the agent factory creates the driver, sequencer, and monitor and new constructs the analysis port. While still in the build phase, the agent calls the getVIF method, which is shown on the next slide. In part 2 of the FIFO agent, the agent's connect phase connects the driver to the sequencer, and the agent's VIF handle is copied down into the driver's VIF handle. After that, the monitor's analysis port is connected to the analysis port in the FIFO agent, and the agent's VIF handle is also copied down into the monitor's VIF handle. The getVIF method called from the previous slide is used to retrieve the virtual FIFO interface handle from the UVM config DB and save it into the virtual FIFO interface VIF handle also declared on the previous slide. So if we put all the pieces together and trace the path of the reactive sequence and the transactions that it generates, the test starts the sequence on the environment agent sequencer, and the driver gets a transaction from the sequencer and drives the transaction inputs as stimulus to the DUT. The monitor samples the inputs on the active clock edge and samples the outputs at the end of the cycle just before the next active clock edge. Then the monitor reassembles the sample transactions into a transaction and broadcasts the transaction to the other components in the environment, including the response TLM analysis FIFO, which will queue up the broadcast transaction, and the sequence that has previously done a blocking get command now wakes up and grabs the broadcast transaction, examines the sampled output status bits to calculate a new transaction to be driven to the DUT. So now let's look at the reactive sequence base class, because this is the key to understanding how this reactive sequence technique works. So please wake up and pay attention to this overview slide. This slide gives a preview of the key features and requirements of the reactive sequence base class. First, the reactive sequence base class must declare a UVM TLM analysis FIFO handle and go get the handle for the response TLM analysis FIFO that was stored by the environment. Now this sequence base class has a handle to the response TLM analysis FIFO that appeared to be dangling in the environment. The sequence base class will define a pre-start method that uses fork join none to spawn off a free-running forever loop. The loop just runs forever, waiting to get the next broadcast transaction from the response TLM analysis FIFO, and because this is a blocking get command, this serves as the first synchronization point, waiting for the next broadcast transaction that will have the sampled output status bits, which are needed to calculate the next stimulus to be driven. After getting the next queued transaction, the sequence base class triggers an event that is declared in this base class. This is a synchronizing event that will notify any sequence command that is running that the sequence now has a copy of the broadcast transaction and is ready for the sequence command to examine the outputs and calculate the next command. So this is just a forked forever loop that gets the next broadcast transaction and triggers an event that will be used by command tasks to synchronize the completion of the current command, calculate the next command, and start the next command. Sequence base classes often contain command tasks that can be executed by sequences that extend from this base class. Since the transactions will be randomized, the sequence base class also includes a randomized fail macro that can be called to display a common fail message in case of randomization failures. Each of the coded command tasks must drive stimulus, wait for the monitor to broadcast the sampled outputs up to the response TLM analysis FIFO, and then wait for the forever loop to execute the synchronizing event trigger, then examine the sampled outputs and react to the outputs by calculating the next command to call. This FIFO-Seq base class is doing most of the hard work. Other sequences will extend from the FIFO-Seq base class and have the required synchronizing mechanism already in place and ready to execute. The FIFO-Seq base class code is shown on this slide and the next. The sequence base class declares and factory creates a FIFO trans object handle and declares a FIFO trans response handle for storing the sample transaction that will be broadcast through the response TLM analysis FIFO back to the sequence. The FIFO-Seq base also declares a UVM TLM analysis FIFO handle and declares a response TLM analysis FIFO event for synchronization. The FIFO-Seq base also declares a pre-start task with a get command to retrieve the response TLM analysis FIFO handle from the UVM config DB and uses fork join none to spawn off a separate free-running forever loop that performs the necessary synchronization between the broadcast transaction queued up into the response TLM analysis FIFO and the command task that is waiting for the response to calculate the next command task. Each sequence defines a main body task, and each sequence can have a pre-start and a pre-body task that can execute prior to the execution of the body task. So which should be used, the pre-start or the pre-body task? Upon reading the UVM class reference, we notice that the pre-start task is always executed, but the class reference mentioned that there are conditions when the pre-body task is not executed. So we chose to use the always executed pre-start task in the reactive sequence base class definition. As we continue the examination of the reactive sequence base class, this slide shows the code that is used for the reset command task. The reset command task executes the typical start item, randomized with reset asserted, finish item commands, which sends the randomized transaction to the DUT, and then waits to synchronize to the broadcast response transaction. The synchronization is set up as a do-while loop, where the do portion is waiting for the synchronizing event, which indicates that a broadcast response transaction has been placed on the response TLM analysis FIFO, and the forever loop gets that response transaction and then triggers the response TLM analysis FIFO event. When that happens, this do command will recognize that the event was triggered, and the while portion checks to make sure that this is the expected reset response. Otherwise, it will again loop and wait for the next triggered response event. The synchronizing handshake details are shown on the next slide. There are two tasks in the FIFO-Seq base class that interact with the response TLM analysis FIFO to make the synchronization work. The pre-start task is where the free-running fork join none loop is spawned. So the sequence base starts the forever loop. Then one of the sequence command tasks is executed from the main body of an extended sequence. The called command task will send a transaction through the driver and on to the DUT. After sending the transaction, the command task now waits for an event to signal that a broadcast response has been retrieved. The monitor samples the DUT inputs and outputs and copies the signals into a transaction that is then broadcast to the other components in the environment, including the response TLM analysis FIFO. The forever loop wakes up and retrieves the sample transaction from the response TLM analysis FIFO and triggers the synchronizing event, which triggers the command which was waiting for the triggered event. the command task checks a specific signal to confirm that the response corresponds to an expected response for this command, and once confirmed, the command task exits the do while loop and the sequence calls the next command task. A quick examination of the base sequence write commands shows that there is a base write command which will be called by the other write command tasks. The base write command waits for the response trigger and keeps looping while this is not a recognized write command. The write until full command task continues to call the base write command while the FIFO response full flag is still low. And note that the subwrite commands do not need to wait for the response trigger. That is handled by the base write command, which is called by the subwrite commands. The write until almost full command task continues to call the base write command while the FIFO response almost full flag is still low. And finally, the write until not almost empty command task continues to call the base write command while the FIFO response almost empty flag is still high. Similarly, there is a base read command task that will be called by the other read commands. The base read command waits for the response trigger and keeps looping while this is not a recognized read command. The read until empty command task continues to call the base read command while the FIFO response empty flag is still low. And just like the subwrite commands on the previous slide, the subread commands do not need to wait for the response trigger. And the read until almost empty command task continues to call the base read command while the FIFO response almost empty flag is still low. We have included a write read command task that can perform simultaneous write and read operations. The write read command waits for the response trigger and keeps looping until both write and read control signals are recognized. We also included a generic do item command task, which randomizes the write and read control signals and executes the appropriate command based on the random values generated for these control signals. With the FIFO Seek base class and command tasks coded, an extended FIFO sequence will inherit the synchronizing pre-start method and execute the following commands. First, a reset is issued for 2 cycles. Then the FIFO is written until full and read until empty. After the FIFO is empty, it is written until it passes the almost empty threshold, and then 6 random write-read operations are executed on the FIFO. Next, the FIFO is written until almost full, and 10 additional write-read operations are executed on the FIFO. After the FIFO is written until full, a random number of additional write operations are attempted to see if the FIFO will overflow. Now the FIFO is read until almost empty and then filled again. Next, the FIFO is read until empty and a random number of additional read operations are attempted to see if the FIFO will underflow. Finally, the FIFO is written until almost full, followed by the execution of 100 more random write and read operations. To summarize the requirements for this reactive sequence technique using a response TLM analysis FIFO, the environment will declare and build a response TLM analysis FIFO. The environment then connects the analysis port of the FIFO agent to the response TLM analysis FIFO and stores the response TLM analysis FIFO handle in the UVM config DB. The response TLM analysis FIFO appears to be a dangling component in the environment, but it is not. The sample transaction is broadcast from the FIFO monitor and is stored in the response TLM analysis FIFO. The FIFO Seek base class declares a UVM TLM analysis FIFO with handle name response TLM AF, retrieves the response TLM analysis FIFO handle and copies it to a locally declared response TLM AF handle. The FIFO sequence base uses the pre-start method to fork off a synchronizing forever loop, and uses a blocking get and triggered events to synchronize command activity. On behalf of myself and my co-authors, we thank you for attending this presentation, and we also thank our friend Josh Wrench for reviewing and providing feedback on both our paper and the presentation slides. We are now willing to answer any questions regarding this reactive sequence technique.